Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll work out some more numerical examples on columns to explain the usage of Rankine's formula. Let us start with a numerical example. A hollow column of cast iron whose outside diameter is 200 mm has thickness 20 mm. It is 4.5 meter long and is fixed at both ends. Calculate the safe load by Rankine's formula using a factor of safety of 3. Calculate slenderness ratio and the ratio of Euler's and Rankine's critical loads. Take sigma c is equal to 550 Newton per mm square, alpha 1 by 1600, E is equal to 8 into 10 raised to 4 Newton per mm square. So it's a column having 4.5 meter long and fixed at both ends. Its outside diameter is 200 mm and thickness of the metal is 20 mm. Now you have to use both Rankine's and Euler's formula and compare it. So you are given length as 4.5 meter or 4500 mm. D naught outside diameter is 200 mm and thickness is 20 mm. So from that you can find out the inside diameter as D naught minus 2T. Alpha Rankine's constant is 1 by 1600 and sigma c, the stress at which the column crushes, is 550 megapascal. Young's modulus of the material 8 into 10 raised to 4 Newton per mm square and column N condition is fixed at both ends. Factor of safety is equal to 3. Let us work out. Since both ends are fixed, effective length of the column L is equal to L by 2. So that is 4500 mm. 4.5 meter means 4500 mm divided by 2, or you get 2250 mm. First you should find out the inside diameter. Outside diameter is given 200. Inside diameter will be 200 minus thickness you should reduce on either side. That is 200 minus 2 into 20, that is 200 minus 40 or 160. So inside diameter DI is 160 mm. So now you can find out the area of cross section 5 by 4 into D naught square minus DI square, or substituting for D naught and DI you will get 11,309.734 mm square as the area of cross section. Moment of inertia of column cross section is given by I is equal to 5 by 64 into D naught to the power of 4 minus DI to the power of 4. Now you can substitute D naught and DI and you will get the moment of inertia of the column cross section as 4.637 into 10 raised to 7 mm to the power of 4. So this is with respect to x-axis, centroidal x-axis or centroidal y-axis, it has the same moment of inertia. So moment of inertia with respect to both the axes we have same. So this can be taken as the moment of inertia of the column cross section. Now you can calculate the radius of gyration k as root of I by a. I we have calculated and area also we got. So substituting that you get the radius of gyration as 64.031 mm as the radius of gyration of this column cross section. Now Euler's buckling load you can calculate P as pi square EI by L square. So pi square into Young's modulus is 8 into 10 raised to 4. I value is 4.637 into 10 raised to 7 and effective length is 2250. Substituting that you will get the crippling load or buckling load as 72,32,041.8 Newton or 7,232.041 kilonewton. So this is the buckling load given by Euler's formula. but we did not check whether it's a long column or short column. We have used Euler's buckling load without checking whether the column is long or short column. In fact, we need not check that because we are directly asked to compare the load given by Euler's and Rankine's. Now let us find out the Rankine's load. Rankine's failure load is given by PR is equal to sigma Ca divided by 1 plus alpha into L by K square. Sigma C is 550, area you can substitute, and alpha is given as 1 by 1600, and effective length is 2250, and least radius of gyration 64.031. Substituting that, you will get the failure load using Rankine's formulas 35 lakhs 10,915.7 Newton or 3,510.91 kilonewton. So this is Rankine's failure load. Now if you compare these loads, you can take the ratio and check the ratio of Euler's load to the Rankine's load. Okay, PE by PR, if you take, that is PE we got 7232.041. Now PR Rankine's load you are getting is 3510.91. If you take the ratio, you are getting 2.0599. So there is a lot of deviation between the loads given by these two equations. So that indicates the formula which you have used, the Euler's load which you have used for this column may not be applicable for this column. So the deviation shows that it might not be a long column, it might be a short column. To check that, you have to find out the critical value of slenderness ratio, that is root of pi square E by sigma C. You can check critical value and compare with the slenderness ratio of this column. So this might be a short column and Euler's formula may not be applicable here. So but Rankine's load always gives a reliable load which will always lies between the load given by Euler's formula and formula given by a short column, that is TC is equal to sigma Ca. Now if it is a short column, the actual failure load you can calculate as sigma Ca, but Rankine's always gives a reliable load in, that is, which lies between the values given by crushing load for short column and buckling load for long column. So this can be taken as a reliable solution for finding out the failure load. And always we use a factor of safety like 3 or 4, so the load applied on the column will be much lower, and some approximation in the failure load will not make much safety issues. So let us work out another example. A column with a symmetrical I section shown in figure is 9 meter long and is hinged at both ends. Find the buckling load the column can support using Euler's formula. Compare it with the load given by Rankine's formula. Given E is equal to 205 kilonewton per mm square, yield stress of material is equal to 480 megapascal. So column is 9 meter long or 9000 mm, and it's having a symmetrical I section which is given here. The size of the flanges is 150 mm and here again 150 mm, and thickness is 20 mm. Thickness of the flanges and web all 20 mm. So this is symmetrical I section. If you take as x-axis, this portion and this portion are symmetrical. Size of flanges are equal and thickness also same. So that makes it symmetrical with respect to x-axis. Now if one of the flange is bigger than the other, then it makes it unsymmetrical. So it's a symmetrical I section with B, capital B means 150 overall width and overall height 140 mm. So this height is 140, 100 plus 20 plus 20, so 140 mm. thickness everywhere, web or flange. If you take thickness is 20 mm, and h, small h I used for the height between the flanges, so that is 100 mm. Now Young's modulus is 205 kilonewton per mm square, so 205 into 10 raised to 3 Newton per mm square. Sigma C is given as 480 megapascal. It's yield stress for 480 megapascal. Column is hinged at both ends, so effective length can be used as a length of the column itself. So let us work out. Effective length of the column L is equal to L, or 9000 mm. Area of cross section. So this is a column cross section. It's in the form of I section. So you can calculate the total area. So area has to be calculated as 3 rectangles, but 2 rectangles are of same size. 150 into 20, a top flange, and bottom flange 150 into 20. So 150 into 20 into 2, that will give the area of both the flanges, and the web portion you have 100 into 20, 100 into 20. So total area of cross section is 8000 mm square. Now to find out the moment of inertia of symmetrical I section, we can use a formula like given for a box type column. So with respect to x-axis, so moment of inertia of this symmetrical I section with respect to x-axis, we can use a simplified formula like which I given for a box type column. So Ix is equal to bh cube by 12 minus bh cube by 12, where b and h are overall size, base is 150, overall height is 140. So b is this overall base size, and h is the total height. So b and h. Small b is the flange length minus web length. So that is this removed portion. From a full rectangle, this portion is removed. So if you combine this empty region, okay, so that will give small b. Or if you take the total length and subtract the web thickness, that will give small b. Or 150 minus 20, that is 130. So small b is 130. B is 130. Okay, 150 minus 20. So that is small b. And h is the distance between the flanges, that is small h. So this formula can be used for only for symmetrical I section with respect to x-axis. Symmetrical I section, to calculate the moment of inertia with respect to x-axis, you can use this formula. So 150 into 140 cube by 12 minus this distance 150 minus 20, that is 130 into height 100 cube by 12. So which will give the moment of inertia with respect to x-axis as 23.467 into 10 raised to 6 mm to the power of 4. Now with respect to y-axis also you can find out the moment of inertia. That we need to check. We have to select the least moment of inertia. So we got with respect to x-axis, centroidal x-axis. Now with respect to centroidal y-axis, we have to find out the moment of inertia of the column cross section. Now the moment of inertia with respect to centroidal y-axis, you can consider this as 3 rectangles. One rectangle, this top flange and bottom flange, both are similar. And with respect to the centroidal y-axis, you can take the moment of inertia as hb cube by 12, height of that flange into base cube by 12. So that is the moment of inertia with respect to y-axis for that rectangle. So hp cube by 12 for that is 20 into 150 cube by 12. 20 into 150 cube by 12. That is with respect to y-axis for that. Height into base cube by 12. And even for this base flange, it is same formula you can apply. So height into base cube by 12, or it is 20 into 150 cube by 12. So these two have the same moment of inertia with respect to centroidal y-axis. So you can club that and you can multiply by 2. So 20 into 150 cube by 12 into 2 plus for this rectangle height is 100, base is 20. So 100 into 20 cube by 12. It is HP cube by 12. So 100 into height is h, base is 20. So 100 into 20 cube by 12. So which will give the moment of inertia of this I section with respect to y axis. So you are finding out the moment of inertia with respect to centroidal y axis of that area, and again moment of inertia of this with respect to its centroidal axis, and moment of inertia of the base with respect to centroidal axis. Since centroidal axis of each area coincides with the common centroidal axis, you can add all the three values. So that will give the moment of inertia with respect to centroidal y axis. So it is 11.317 into 10 raised to 6 mm to the power of 4. And we can see that this value is a least value compared to the other value. So this is higher, and with respect to y axis you have least value of moment of inertia. So with respect to y axis it has got the least moment of inertia. So the column, if it buckles, it has to buckle in this direction. This way it should buckle, and that is perpendicular to y direction should buckle. So it cannot buckle in the perpendicular to x axis. This direction it has got more resistance to buckling. So easiest way for the column to buckle is perpendicular to y direction towards x direction. Now this is selected as a least moment of inertia. Iy is selected as least moment of inertia, 11.317 into 10 raised to 6. So least radius of gyration is root of I by a. I is least moment of inertia, 11.317 into 10 raised to 6 divided by area of cross section. We got 8000 mm square. So substituting that, you will get the radius of gyration as 37.612. So that is the least radius of gyration of the column cross section. Now Euler's buckling load you can calculate as P is equal to pi square EI by L square. Pi square EI by L square, or pi square into Young's modulus is 205 into 10 raised to 3. I values least moment of inertia 11.317 into 10 raised to 6, and effective length is 9000, column length itself 9000 square. So you get the Euler's buckling load as 2,82,683.14 Newton. So that is 282.68 kilonewton. So that is Euler's buckling load for this column. Now here Rankine's constant is not given in this problem, but Rankine's constant, whenever it's not given, you can calculate using the formula sigma c by pi square e. This Rankine's constant. We are given the sigma c value, and Young's modulus is also known. So by substituting sigma c by pi square e, you can calculate the Rankine's constant. So Rankine's constant is 0.000237. Now you can find out the Rankine's failure load. So Rankine's failure load is sigma ca divided by 1 plus alpha into L by k square. Sigma c is 480, area of cross section is 8000, and alpha you can substitute, effective length is 9000, and least radius of gyration is 37.612. So substituting this, you get the failure load given by Rankine's formulas 2,63,347.89 Newton, or 263.35 kilonewton. Now this is a failure load given by Rankine's formula. Now these two values are nearly, there is a load given by Rankine's formula and buckling load given by Euler's formula are very close, and if you take the ratio of Euler's load to Rankine's load, P by PR, you will get it as 282.68 divided by 263.35, or 1.073. So they are in very close agreement, both the formulas, but they will not be equal No point of time these two formulas will give equal values, but always PR, the Rankine's load, will be a compromise between the load given by both the formulas, but it gives a reliable answer for any type of column. We need not check what type of column it is. We can apply Rankine's formula to find out a failure load. It's a quick way of finding out a solution to the failure load for a given column, whether it's a short column or strut or a long column. You can apply Rankine's formula. We can check that by finding the critical value of slenderness ratio for the given material, and also checking the slenderness ratio of this column. You can compare it and decide whether it's a long column or short column, and this might be a long column. That's why the Rankine's load has become very close to the Euler's load. That's all for today. Thank you for watching.